Hello everyone. In this video we are gonna talk about free vibrations problems. The objects that we're gonna talk about, the parts, are gonna be columns, beams, and frames, the axial members. So in one of my previous videos you have seen the static analysis on them, and we found the stiffness matrix K. So what we are going to do today is we're going to use that result, and we're also going to find the mass matrix M, and then using those two we can find the natural frequencies of these different systems. So the equations we are going to use for modeling is the Lagrange's equation, which as you know, it is the time derivative of partial of kinetic energy with respect to the generalized velocities q dot minus partial of kinetic energy with respect to generalized coordinate q plus partial of potential energy with respect to q. In general, this is like equal to the generalized forces qi, but for free vibrations we don't have any force from outside the system, so the right hand side is 0. And again, here this is your potential energy, this capital lambda, right? And your T here is your kinetic energy. So what we'll do is we start with columns, and here we have parameter gamma, which is mass per length. So gamma here is m over L. And if you remember, we only have 1 degree of freedom at each node, ui and uj. And your axial displacement is written in terms of the dot product between the u vector, the nodal displacement vector, and the shape functions, where the shape functions were 1 minus x over L and x over L, where x was the local coordinate. And so kinetic energy is clearly the integral over the whole length of half of gamma times u dot squared dx, right? Because if you remember, kinetic energy is 1/2 mv squared, right? That's the term for kinetic energy, 1/2 mv squared. And in this case, we divide that by L here, and instead of that we have m over L, which is gamma, so it's gamma over 2, and then u dot here is the same as v. So this kinetic energy is also calculated per length. And so we integrate this kinetic energy term gamma. You can count it as constant, bring it out of the integral, and then u dot is going to be time derivative of this, where here the s's are not functions of time, so these nodal displacements, you take them time derivatives, and then that's your u dot, and then you square it. Then you can find the component that you need in the Lagrangian equation, the first two terms. And here I'm showing you how to calculate basically the first term here, right? And you can see that here we take partial derivative of t with respect to u dot I and u dot j, and then take time derivative of those, right? So definitely these are going to be integral terms that you have to have. And then you also have this term here that you have to calculate. Now in our case, if you look, t has no derivative with respect to ui and uj, right? It's just u dot I and u dot j. So this term for our case is clearly 0. And then this last term here, this potential energy derivative with respect to q, this is going to be the conservative force, which is going to be like a k times u in general. Okay, and this k is the exact same k, the stiffness matrix, that we derived when we did the static analysis of the columns. So this K I already have. I don't need to calculate that. And this K is basically this matrix that I already derived for columns. So the only term I really need to focus on is this first term here. That's the only term I need to focus on. And here you see that I wrote these terms, and then you perform the integrals, where the integrals are done over the SJs and SIs and the products of them, right? Because this UIJ and UJ double dot, they have no functionality with X. So if you simplify the integrals, it involves a little bit more algebra, and you can do that, or you can refer to the textbook for it. If you simplify, then you can derive the mass matrix as well. And the mass matrix is going to be gamma L over 6, 2, 1, 1, 2. Okay, so this is your mass matrix. And your system is going to be reduced to this equation here, mu double dot plus ku equals 0, where ku comes from this last term, and mu double dot comes from what? Comes from the first term. And as I said, the second term is 0, and qi in this case is 0 because it's free vibrations. Okay, so this is going to be your final equation, which is clearly free vibrations equations, and this is m and this is k. Now if you want the natural frequencies, what you need to do is to invert m multiplied by k, and then the eigenvalues of that are the square of the natural frequencies. So if you take the square roots of the eigenvalues of m inverse k, those are going to be your natural frequencies. And then the eigenvectors of that are going to be the mode shapes of the system. Now here we are mostly after the natural frequencies, but if you want mode shapes, then you want what? You want the eigenvectors of this matrix. So eigenvectors of this matrix are your mode shapes. Okay, so this is the M matrix, this is the K matrix. Now, if you look at the beam, remember it had 2 degrees of freedom at each node, a vertical and displacement and a rotation, and you could write the total vertical displacement at any point as a linear combination of the mode shapes and the nodal displacement, where the 4 mode shapes are these 3 functions. These 4 functions that we learned when we talked about beams. Again, t per length is gamma over 2 the velocity squared dx, and that's going to be this guy. Here you have to take time derivatives of u dot, which you have shown here with ui1 dot, ui2 dot, uj1 dot, uj2 dot. And then you have to integrate these s's when you square them and do product of them, and you integrate. And then you have to take the derivative of the result with respect to u dot, take time derivative of that, so it gives you mu double dot. And if you perform all of that, this is going to be your M matrix. And your K, again, this comes from the lecture we had on the beams. This is that stiffness matrix we derived. That's the exact same thing. And this is your M matrix, the mass matrix, okay? And these 2, again, we can use to get the 4 natural frequencies of the system, each one for one of these degrees of freedom. Okay, and then, or basically, not each one, what you have is really 2 of them for the vertical deflections and 2 of them for the rotations. So mode shapes 1 and 2 for each one. Now, if you look at frames, remember, they can have an angle in general. The members can have an angle like a truss. And for them, we had this transition matrix, which will take us from one frame to another. It will take us basically between the local frame and what? The global frame here, right? So your old frame, or your global frame, is basically, in this case, since this should be negative, that should be positive, it's going to be T inverse. So U capital in this case is T inverse times U, or U small is T times U, basically. Okay, so this T will take you from global to local, and that's in local frame that you formulate the kinetic energy. The K matrix in the local frame is this guy. We derived this already. in the past, and if I want to take this local K matrix to the global frame, I use this transformation, which, if you remember, I called this in the past a sorry for my bad handwriting, really. We call this a similarity transform. Okay, and then here, so you have T, you have K. You can find the global K. Then you need to again form the kinetic energy. And by the way, this T here and this T are different T's. Okay, so that might not be necessarily a good idea to call it T. I don't know, because you see, I have a transformation matrix and I have this kinetic energy. I call both of them T. Now, of course, one of them is inside the matrix and the other one is a scalar quantity. Okay, but again, just keep in mind, this one, scalar, is kinetic energy. This one in matrix is, in this case, a transformation matrix. So the M matrix here, you can derive it and you can show it's the 6x6 matrix. And you can take this M matrix local and take it back to the global frame using the same transformation that you applied to K, you can apply to M. So if you want kinetic energy in this system, of course, it's going to be all of the degrees of freedom together, right? So your kinetic energy, I don't want to derive anything, but your kinetic energy is basically gamma over 2, the integral from 0 to L of then you have ui1 dot si1 plus ui2 dot si2 plus dot 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 plus all the way to basically uj3 dot sj3 integral dx. Okay, so you have the 6 shape functions multiplied by the nodal velocities, and then this one should be squared, and then that is your kinetic energy in this case. So you have to simplify it, and that will give you this mass matrix. And as I said, the static case will give us this K matrix, both 6x6. So now let's use them for solving a real problem. In this case, we are going to look at a frame, and I said let's use the one with the largest matrices. So we're going to look at a frame that has 3 elements, element 1, 2, and 3, and 4 nodes, nodes 1, 2, 3, 4. And the length of these members are 15 and 20 feet. The I and the A for members 1 and 3 are given here, and the I and A for member 2 is given here. Okay, and you also have the depth for them. The E is 3E to, I assume this should be 3E6, not 5. PSI and gamma is, for this material, is 0.0056 pound second squared over inch squared. Okay, and you want to find the natural frequencies of the system, or is pound mass per inch if you want. Now, what we have here is for elements 1, 2, 2, 3, and 3, 4, the angles are 90 degrees, 0, and 270, right? Because the vector here is like this. This is your local frame here. That is X, and this is Y. Right, so you see clearly with respect to the horizontal axis, you have a theta of 90 degrees. In this case, this is your local frame, which is the same as the global frame, so theta is 0. And in this case, this is your local frame, right? And you want to make sure that actually in this case, let's see, a Y goes here, right? So this is X, this is Y, and in this case, this is X, and this is Y, right? So the angle is basically this whole thing here, which is 270 degrees. That's that is going to give us the T matrices, the transformation matrices. This is transformation for element 1. This is transformation for element 3. For element 2, since the angle is 0, your T is simply going to be an identity matrix. Next, we go and look at the K matrices, the K locals. Now, for element 2, K local is the same as K global, right? Because the orientation of local and global are the same. For elements 1 and 3, then the xy, like element 2, comes from this formula that we had, and then we apply the similarity transform using their own respective t's, and that is going to give us some different global k compared to what? Local k. So this is the global k of element 1, this is the local k of element 1, right? And you see the numbers are different. The same thing goes for 3, but for 2, k global and k local are the same. Then we go to M matrices. Again, we have the formula for M matrices, and we calculate the local M's for all of them, right? And then these are the M's. Again, for elements 1 and 3, we have to transform them back to global, which is going to give us different numbers. For 2, it's going to be the same. And then we assemble the K's and the M matrices together. So this is going to be my global K matrix for the entire frame. That is global M matrix. Invert M by K, find the eigenvalues, take the square root of them, and that is going to give us 6 frequencies, and they are constantly increasing. And basically each 2 of them are for one type of the shape, right? So they are basically for axial deformations, for lateral deformations, and for rotation deformations. And you have 6 frequencies which are constantly increasing. And as I said, if you want, the eigenvectors of them are the mode shapes for these frequencies, which you can also find from modal analysis in ANSYS. So here now you know how ANSYS is going to find these frequencies for you, or the mode shapes. This is the method for these 3 members. Okay, so free vibration problems, and I would say free vibration of axial members, right? If we want to be very accurate, we have to say exactly what we are doing. Okay, so hopefully the video was useful to you. Now in dynamics problems, right, or force vibrations in transient and structural, this right-hand side is not 0, and there might be forcing functions, and there might be damping forces which you have to add to your system, right? So in general, transient response analysis and transient thermal, as I said in the previous video, are more complicated, which if I have time, I'll talk about them. But these are like the simplest level of problems that you can see here. Thank you so much. I'll see you in the next video.